Everybody okay on pots? What they do, they're really neat. And we used to have a pot around here where you could actually see this. This is a pot that basically works like the little unit that I showed y'all up here, right? You remember that? The little motor. Then we talked about what we call the transfer function. Are y'all okay over there? So what do we do with the transfer function? So what is it? What is the transfer function? So what does a sensor do? Well, we can't say presence of something. Well, what it does is it takes a physical stimuli and converts it over to an electrical equivalent. Okay, but what could that physical stimuli be? It could be weight, it could be color, it could be position. So the transfer function gives you an indication of what the output would be at a certain input, at a certain temperature. Okay, y'all understand? So I got a temperature sensor, and temperature sensors don't output a voltage. They usually change their resistance. So what I got to do is I got to say, okay, how much resistance equals to each degree? Well, when we say how much resistance equal to each degree, then that would be the transfer function. That makes sense? Because I'm over on the output of the sensor side. To determine if the sensor's working, I'm on the output side. And if I go to an output of a sensor like over there and I don't know what it's supposed to measure, right, what does that mean? I don't know if it's good or bad. Now, a lot of times you can tell, most of the time what we do is we come over there, if we got a temperature sensor, we'll put our meter on the output of it and we'll heat it up with our fingers or stuff like that, and it varies. We assume that it's good. But if it's giving us the wrong reading, then it's either something in the unit that's giving us the readout, or it's something we didn't do the transfer function, right? So what this guy right here says, it says a pot is supplied with 10 volts, which is pretty standard for analog signals. The pretty much standard for analog signals is 0 to 10 volts. So what does this guy here say? So what would we do? So it says, okay, I'm trying to figure out, I'm measuring 3.2 volts on the output. What degrees does that indicate? So over here on the input, we're inputting degrees, but the output of my sensor is giving me what? Volts. So I've got to figure, okay, I'm reading 3.2 volts. Is the sensor good or is the sensor bad? Bad. Unless I know the transfer function, it what? Yeah, it don't mean anything to me. So what would we do for the transfer function? Yeah, the number of increments we're going to divide it into. So we got 350 degrees, and we're dividing 10 volts into 350 increments, right? Does that make sense? So my transfer function would be equal to what? Yeah, what the voltage, the output divided by what we're inputting, Rexy. What was that? And that would be millivolts. And then we use the divide sign. So another thing that we use that for stands for per degree. So if I know if I got 25 millivolts per degree, then I would come over here and I'd say, okay, 25 millivolts per degree. What degree is 3.2 volts? So we would come over here and we would rearrange this equation. So where's the voltage at? Up here. Where's the degrees at? Down here. And then here's the transfer function. We know the transfer function and we want to solve for volts. Does that make sense? So we could take this little old formula right here and put it in our little wheel. We can say the transfer function would be equal to volts over degrees. And what am I trying to solve for? Volts. So I'd say, okay, my volts would be equal to the transfer function times what? No, we're solving for degrees. I'm sorry. Yeah, we're solving for degrees. So what would we do to solve for degrees? Yeah, we would take 10 and then we divide it by, no, not 10. No, we would take 3.2, we know the volts, we know the transfer function. I agree with y'all. So we would take what? We would say the what? The degrees is equal to what? The volts divided by the transfer function. So all we're doing is taking this formula and doing what? So what do we come up and get? Right here. So I'm saying this is. I say I'm on the output of my sensor and I'm measuring 3.2 volts. How many degrees does that represent? Okay. What's that? 20? 12. 112 degrees. Yeah, that's what we're doing. So what I'm doing is I'm measuring the output of my temperature sensor. And it's giving me a certain voltage. And we're saying, okay, what degrees does that indicate, right? Y'all understand what we're doing?
As long as you got two. It's just like on.
Yeah, well any three term equation, if you know 2, you can solve for the third. If you know 2, you gotta know 2. And it's just like Ohm's law. It's just like Watt's law. It's just all these laws that have these 3 terms inside the equation. If we know 2, we can solve for what? We can solve for the third. So now this means something to me, right? Now that 3.2 volts means something to me. Or I could come up and I can say, okay, what would the voltage measure at 250 degrees? Well, what am I solving for? Degrees. Let me put a D down there instead of that. I'm solving for degrees, right? Y'all understand that? So what do we know? I know the transfer function, and I know the degrees, and I'm trying to solve for V. So what would I do? I'd say V is equal to what? The transfer function times the degrees. So what would we expect to measure out of this? Huh? Got to give me the voltage that this thing should output. So what we're doing is we're taking a physical quantity, a position, and we're converting it over to voltage, which is very, very popular. Even if a sensor changes its resistance, it's real easy to take a resistor, a sensor that changes its resistance, and make it develop a voltage. So what we would do is we would take the sensor that changes its resistance with whatever it senses, and then we would just set up a little voltage divider. I'm not understanding. So we got a fixed resistor, and then we got a variable resistor. So if this resistance goes down, and I'm taking my output voltage right there, then the output voltage would go down. If this resistance goes up, then the output voltage would do what? Would go up. So we have a lot of sensors that change their resistance, but it's real hard for a controller to sense resistance. It's going to want to sense what? Either voltage or what? Current. But I can take a sensor that changes its resistance and very easily turn it into a voltage. Just by putting the fixed resistor, right, you understand that, and then putting the sensor down at the bottom or the top, depending on which direction you want to go.
You call this, that's wrong. What do you actually call that for?
It's just the, I guess you would say it's the transfer formula. I mean, so the actual formula we're dealing with is the transfer, the transfer function would be equal to what?
Transfer function is voltage divided by 3.
Well, that's 4 degrees. If it was weight, it would be volts per pound, right? Or if it was this, it would be this per pound. So what we do is this is going to be the actual voltage, right? And then this is going to be, I don't know what to put there, what we're converting. So if I had a weight and I had a load cell out there, well, the load cell is going to give me so many volts per pound. So we excite them with 15 volts. So 15 volts would be on the top, right? You understand? And then we would come down and we would say, okay, it's a 10,000 pound scale. So that way you'd say, well, I'd get so many volts per watt per pound. Does that make sense? What we're outputting on will be on the top. The unit we're coming from, we're converting, will be on the bottom, and then you can come up and just transpose it depending on which way you want to go. So this is nothing but the transport. It's out over in is what it is. So the transfer function would be equal to what? Out over in. So if I had a current loop, it would be amps over in, right? If it's this, it would be. Now we said 15 volts, but a load cell it's whatever the load cell outputs when it's putting out its maximum output. A load cell, I can't remember. I need to look that up. I worked on scales for years. We excite it with 15 volts, but the load cell never puts out 15 volts. So if it's a 10,000 pound scale, the maximum output for 10,000 pounds would be on the top. Right? Anybody work with load cells, scales? Yeah, it's not. It's 15 millivolts per volt is what it is. So if you excite it with, that's what I remember. So if you excite it with 15 volts, then the output would be 15 millivolts times the excitation voltage. And that would be the maximum that load cell would put out. Well, you wouldn't put the 15 volts on the top. You would put the maximum the load cell would put out when it's at its maximum load. So load cells can be excited by different voltages when you hook them up. So if you look at a load cell, it's got two where you put power to it, and then it's got two where you get the signal off. Well, you can't get the power because it's powering up the load cell. It goes through a bridge. It goes through a Wheatstone bridge, and we're going to have to learn for sensors. We're going to have to learn about that. It's not that complicated. But this would be the maximum output, basically the maximum output divided by the unit you're trying to convert it into, right? I don't know what to put there. So this could be weight, maximum weight. This could be maximum temperature. This could be all these different types of things. So on the pot, if we got it all the way up at the top, then that would be 10 volts. If we got it on the bottom, it would be 0 because we use 10. But if we come up here and set a span on the thing, and we set this to 8 volts, and then we set this to 3 volts, then the maximum we would ever get out would be what? 8, even though we're exciting it with 10 volts. Does that make sense? So what we do is we use the maximum output, not what you hook up to the thing, the maximum output that you allow the sensor to output. Are you okay? Make sense? Yeah, so a standard load cell is 15 millivolts per volt. So if we hook that thing up to 15 volts, then the maximum we would ever get out of that thing would be 15 times 15 millivolts. So what would be the maximum we would get out of that load cell? And we use 15 volts because every scale I ever worked on, we excited the load cell with 15 volts. So what would be the maximum we'd get out? Not much. Huh? What's that?
Or 225.
Yeah, millivolts. So those things were very touchy. So that if I got a 10,000 pound load cell, when there's 10,000 pounds on top of that load cell is only putting out 225 millivolts.
Excitation.
Well, no, what happens is that a load cell works on the principle of what we call a Wheatstone bridge. And what we do on a Wheatstone bridge is we have two resistors on each side. And then what we do, and I'll put a common down here. And this is where we're going to excite it at right here. But what we do is we take the output right here. Okay? And people don't understand that. So if this was 1K and this was 1K and this was 5K and this is 5K, and I come over here and I put 10 volts on there, what output would I get right there? Well, if this was 10 volts, these are the same size, so that I would have 5 volts right there. These are the same size, I would have 5 volts right there. What would my meter read? My meter reads 0. And that's the way the Wheatstone bridge works. So this would be the sensor, maybe this would be the sensor. Okay. And then normally, when we have a temperature sensor, it gives us an output even when it's freezing. So if I wanted to set it up for the centigrade scale, I would want to get 0 out. I would want to get 0 out when the sensor was seeing maybe 15K on it, right? You understand? So what I could do if I came over here and made this variable right here with the Wheatstone bridge is I could set 0. So now if this thing went up to 15K, then I could come over here and adjust this to 15K, and now I would get 0 out, which would indicate the temperature is what? Is 0. So the ideal thing about a Wheatstone bridge is we have the ability to establish what 0, when the output, when the sensor is giving us an output, it's going to give us an output all the time. So a load cell, when it's set, when there's nothing out there on the scale is still sitting on top of the load cell. So that dang load cell is outputting something when there's 0 weight on the scale. But what's the load cell seeing? It's seeing the weight bridge out there, right? So the weight bridge is sitting on there, so it would output whatever that happened to be. But I need to say, okay, if there's not a truck on the scale, this is 0. So with the Wheatstone bridge, we could do what? We could come up here and we could adjust that. Now what the load cell does is it has 2 sensors, and what it does, the problem with the way a load cell works, and this is about another lesson, it literally works on the size of a conductor. So what happens when you put weight on it, it causes the conductor to get fatter. When you take the weight off, it causes the conductor to get skinnier, which changes the resistance of the wire. Well, the problem is, what else changes the size of the wire? Starts with a T. Temperature. So what we do is we put one load cell in there sideways, so it's sensing temperature. We put the other one up here, and we put them across from each other in that load cell. So it means if the temperature goes up, they go up by exactly the same amount, and the Wheatstone bridge stays balanced. And we set 0 in the scale. We don't set it at the load cell, we set it at the scale. So what happens with the change of the temperature, the Wheatstone bridge out there in the load cell stays what? Stays balanced. So if the temperature goes up, both of them change their resistance. This guy is not looking at weight, it's looking at what? Temperature, and it keeps the thing balanced. So we have a Wheatstone bridge out in the load cell. Well, up here is where we excite it at, right here. That's where we put the 15 volts. But we're not concerned with the 15 volts. We're concerned what is the output at maximum weight. So load cells are rated in millivolts per volt. And what that is, it's how many millivolts you get out by whatever excitation voltage you put on the scale. The load cell, I could put 3 volts on this thing. It don't care. It's nothing but a Wheatstone bridge, right? You understand? So I could put 3 volts. I could excite it with 3 volts. I could excite it with 15 volts. I could excite it with 30 volts. You know, as long as I don't exceed the voltage rating of the unit itself. So load cells, when you buy load cells, they're not given it at an output voltage. They're given as a what? Millivolts per volt. And what's the volts? Well, it's the excitation voltage. But what I'm doing is I'm taking a scale. And what's nice about a Wheatstone bridge is that, first of all, we can set 0, right? You understand? And we can use these other resistors to actually set the span. So Wheatstone bridges are used a lot in sensors, a lot. So we'll look at a little more on this later on. But let's go back and look at some of these, and we're going to have to get. So this is what they're showing. This is using an air amplifier, and we have special circuits. So what's the two main? So we have the voltage, right? And what's the other one that we use? We use what's referred to as a current loop. And I think we got a drawing in here on how that works. It's really neat. Current loops are really a really neat feature because it ignores the resistance of the wire, the way the system's set up. So that means if you get resistance in your wire, as long as it's within the limit of the current loop, it don't care. So we can run current loop real long distances. What we do in here though is you got to understand. So here's the pot, here's the motor. But what are we doing? We're turning it with a gear. So what this means is the transfer function of the pot and the transfer function of the motor, we're going to have to compensate for the watt, for the gear. How would y'all think we would do that? So here we have a big gear turning a what? Small gear, and it's a 3-to-1 ratio. So what does that mean? So for every 1 tooth on the big gear, the little one's going to turn what? 3. Or y'all understand that? Or every inch or so. So what would we do here? So basically, what would I do to do the transfer function? So here's my pot up here. Here's my motor I'm trying to sense the position of right here. Yeah, that's what they're trying to say. So they're giving you an answer. So they say when this moved 270, this guy right here, so I would take 9, and this turns 3 for every 1 degree here, right? So notice what they did. They took the 90 and multiplied it times what? 3. And what's 90 times 3? 270. So when this guy here is indicating 270, so what we would do is, but we could still do the transfer function. So how would I do the transfer function? So let's say up here on my pod I've got 10 volts. Well, that's not the transfer function. So first of all, we need to know the range of the pod. Okay, you understand? So let's say it's the same one we used before. So that way we know the transfer function, right? So let's say it's a 350 degree pod. So the transfer function is not this. That's what this guy is measuring when this is 90 degrees, right? You understand? So the transfer function would be equal to 10 divided by 350. The transfer function would be equal to what? Okay. Okay, we're okay. All right. But what we're going to do is we're going to say, okay, what voltage would I get out when this is at 270 degrees? So here's my formula, right? So the transfer function is equal to the watt. It's equal to the volts. So what over the degrees again? And I'm trying to solve for voltage. Well, let's go the other way. Let's move this. Let's say this is 40. Let's say this is 45 degrees. So what would be the first thing I would do? I'd take my 45 and I'd multiply it times the gear ratio, right? Y'all understand? Okay. And what would that give me? I changed the angle of the. So here they did what? 90, and what we're going to do is figure out if we can figure it out for 45. And we'll do it the other way. So what am I doing now? I'm taking this and multiplying it by the watt year. What do we get? And then what would I do? We're solving for the watt, the volts. So times. So we're solving for volts. So it's a transfer function times this. So multiply it times what? Guess what we're going to do next? I'm going to give you a voltage, and I want y'all to give me the degrees of the motor. 3.8 volts? I don't know. I don't have a calculator. Yes, I do have a calculator. 135. What we got? 3.8? 3.9? Okay. Normally on these we usually carry them out to like 2 decimal points because there's what's 6. Okay, so let's say I came over here on the output of my pot and I measured 7.3 volts. What would be the degree of the motor? That's what we need to know. So what would you do? I would take 7.3
divided by 2.1816.
and that would give you the degrees of the pot, and then you divide that by 3 because we're going the other way, and that would be the angle of the motor. So what was the angle of the motor? Anybody got it, Chip? No, we don't know this.
No.
So we just know that thing is somewhere out here in the no man's land, right? And what we're trying to do is we measured 7.3 volts right here. Y'all understand? And we're trying to figure out what is the motor, not the pot, because we're trying to figure out the position of the motor. So what would I do? Well, first of all, I'm going to find the position of the pot. While ago, going from the motor to the pot, we multiplied by 3. So going from the pot to the motor, we're going to do what? Divide by 3. Does that make sense? So first of all, we would calculate the angle. So here's the degrees. What's the degrees equal to? D would be equal to what? 7.3 divided by 0.6 milli. So what? Okay, and then, but I want to know the, now multiply by. Huh? I've hit the part where I can't write it anymore. So this is what we have to do with analog sensors, right? You understand that? We got to figure out what the sensor outputs to represent what quantity is intended to measure. Then if I can do this, then I can figure out if the sensor is, so transfer function is equal to what? Out over in. This right here is going to be the physical, right? And this is going to be the maximum output. So your sensor is going to be given a maximum range for it. And the maximum the range is, that's what you're going to put on top. The maximum you can possibly get out of that sensor when it's measuring what it's supposed to measure, divided by the physical things of the scale, like the 1,000-pound truck scale. You know, we had a 180,000-pound rail scale that we worked with, and it was a single axis, so it's just one axle of the scale. It was an axle scale. And what it is, if you got two 100,000-pound load cells on there, then the scale is a 200,000-pound scale. because because the weight is distributed on the bridge, which is pretty nice. I'll see if there's this is the only problem we have with a pod. A pod is not perfectly linear. So it has this little S curve to it. So if I wanted to have extremely precise position measurements, I would not use a pod. That makes sense? No, Tegr's available. See, I got to go right here. It's just that Tuesday's not up there yet. I didn't have access to the Integrity for this class on Tuesday, but I recorded it somewhere else, I think, and I'll copy it over. Can y'all do this one? A single turn 350-degree pod has a linearity area of 0.1 and is connected to a 5-volt DC source. What would be the maximum and the minimum error we should expect? So when you buy a pod, a lot of times it gives you what they call the linearity error. So it don't mean it's bad. It just means this would. So we could be off by what? Yeah. So they're really good. You got to understand, but they're not exactly. So what you would do is you'd calculate the. And then it could be off, yeah, by 1% of that, right? Everybody okay there? So 0.1% is not too shabby, but it's still not perfect. No, we don't need this. What about ADC, what is ADC? So when we bring this thing into an analog to digital converter, it's either a 2-bit, it's either a 1-bit. So when we look at a binary number, it's made up of nothing but ones and zeros. And this is the beauty about binary, is that we can represent it so easily. Here we could use voltage, right? So we can use voltage to represent it, or we can use current to represent it. The analog to digital converters that either is a 1, and we call each one of these digits, these are digits, we call these bits. So a 1-bit analog to digital converter can only give you 2 states, right? Either what? True or false, off or on. But it's real easy to represent. You know, we could use 5 volts for a 1 and 0 volts for a 0, or we could use 0 for a 1 and 5 volts for a 0. It's basically relative to what we need to control. But if I'm trying to get the temperature, then what I need to do is I need to take that analog output and convert it into more than 1 bit. Does that make sense? Right? So when we get into binary, well, let's play around with that a little bit. First of all, me as a person, I do real good with binary because I've dealt with it so long. But the average individual, when you look at a binary number and you look at this number that's big like that, and right off the bat you think that's a big number. Because we see it as what? We see it as base 10. We see it as base 10. But base 10, every digit in the base 10 or decimal number system has 10 combinations, 0 through 9. The digits in a binary number only have 2 combinations, 0 and a 1. So it means it's going to take a lot more bits to represent numbers in the binary system. So here it says we've got an 8-bit digital analog converter. So that means we would have what? It means we would have 8 bits. Now, what we do in any numbering system any numbering system, we can figure out the number of combinations we have depending on the number of digits we use. So every numbering system, true numbering system, has what we call a base. Anybody know what the base is? What is a base of a numbering system? Basically, it moves in those powers, but basically that's the number of combinations a single digit can have. So in base 10, each digit could have 10 combinations, 0 through 9. Okay? Does that make sense? Yes or no? So what we can do to calculate the maximum number of numerical combinations we can have, we can take the base and raise it to the number of digits. So if I've got 2 digits of base 10, I can have 10 squared, which would give me 100 combinations. 0 through 99. Everybody keeps forgetting about 0. 0 is a numerical combination. It just don't have any weight, right? You understand? To calculate the actual maximum weight we can represent, the formula is base raised to n minus 1. So if I have 2 digits of base 10, that's 2 squared. That's what? 10 squared. That gives me 100 minus 1 means the maximum number I could represent with 2 digits of base 10 would be 99. So if we got an 8-bit analog to digital converter, the number of combinations we can represent would be 2 to the 8th. The base, y'all understand that? The base on how many combinations can each bit have? It can only have 2, right? Y'all understand that? So after a while, and powers of base 2 powers are real easy to figure out once you learn them, because they go like this. It goes 1, then it goes what? 2, then it goes 4, then it goes 8, 16, 32, 64. 128, 256, 5, 12, 1,024, 2,048, 4,096, 8,192, 16,384. Now see, I've dealt with this a long time, right? So they keep increasing, but you start with 1, and what do you do every time? You double it, right? You understand? Well, what we would do to calculate the number of combinations, 1, 2, 3, 4, 5, 6, 7, 8. So this would be what? 128. Now, if we put a 1 in every one of these, it would come up to be 255. But what we can do is we can come up here and just count the number of digits, 1, 2, 3, 4, 5, 6, 7, 8, and we take what? 2, and raise it to the what? Number of bits, right? And 2 to the 8th would be the next one past this, which is what? 256. So what we're going to do is we're going to bring in an analog signal into the input of the A to D converter. An 8-bit AD converter, we convert it into a binary number, an 8-bit binary number that represents that quantity. Anybody know how to go from binary to decimal? Yeah, so what we would do is we would come in and take just a random number, and we got calculators that do this for us now. We'd start off and go what? What do we do next? Add the ones. So what would I add? 128, 32, and 11. So that would be the weight of that number. So I could take an analog input to this thing, and it would give me the binary equivalent of that, right? You understand? So let's say I have a device that outputs from 0 to 10 volts. What binary number would it give me for if we inputted a 3? Well, what we need to do, it's not going to give me a D. It's going to take, what it's going to do is the maximum it could put out is 255. That will represent 10 volts. You understand? So just because you put 3 volts into it, that's relative to 100. That's not relative to 10 volts, right? You understand? So the first thing we got to do is calculate the transfer function. So we're getting binary out, right? So this is going to be backwards. We're putting voltage in and we're getting binary out. So what we got to do is figure out how we're going to take that 10 volts and what we're going to divide that 10 volts into. So this is not really a transfer function. Or would it be? God, right. So how would we do this? So I'm going to take 10 volts and I'm going to divide it into 256 steps. So somebody give me an idea on that. Now we're not dealing with 3 volts. What we deal with is we deal with the maximum output. Okay, so 10 volts is the maximum. So when this guy sees 10 volts, the output of my A to B converter is going to be that. It's going to be all ones. Somebody make some sense of this one. No, it won't be. Because that would be if 10 equals to 10. 10 don't equal to 10 on the output of that A to D. 10 equals to 255. So if I put 10 volts into it, I don't get this out of it. That would be a waste of a lot of bits. So you're looking in your mind, you're saying, okay, if I put 10 volts into it, I get that on the output. That's not true. When I put 10 volts into it, I get that. Right. So that means if I put 3 volts in it, I'm not going to get a 3. Because if it gave me a 3 when I put 3 volts in it, then it would give me a 10 when I put 10 volts into it. But it don't. It gives me 255 when I put 10 volts in it. So no, it's not going to give me a 3. It's going to give me a binary number relative to 255, right? You understand? Yes or no? And it's the resolution. We got 10-bit A to D converters, which would divide it into 1,024 steps. We got 12-bit A to D converters. These would have better resolution. Because what we end up with is this output is going to step on us. So what that means, if I put in 3.23 volts out there, we probably don't have a binary number that represents that. So A to D converters are not perfect, right? You understand? It's just like when you get out of the range of your meter. So your meter drops off somewhere, right? So your meter can't see, 500 and you can't see 5.678325 volts out here because your A to D converter does not handle all those fractions out there. So somebody give me an idea. What's the biggest thing we can represent? What does 255 mean? Means 10. 10. So what I'm going to take 10 and divide it by 255.
39.2.
What's that? So we would say that's 39.2 millivolts per step.
255 though.
Huh? No. Then I'm going to say, okay, what voltage am I inputting into this? We're going to do 3. Okay.
So 3 divided by 39.2.
75.
What's that?
3 divided by
39.
75. I got 75.9.
Well, what you got to understand, we don't do fractions. My binary number has no way of representing a fraction.
76.
Okay, so 76.
Then we go binary.
And then we would take 76 and convert it to binary, and that's what we did. Y'all know how to convert to binary?
Started at 64. That's the highest number.
Yeah, what we do is we always go one past the number to make sure that I have enough, right? So I go 1, 2, how's it go? 4, 8, 16, 32, 64, 128. And now I look at my 75. And I look and say, okay, what's the biggest one of those weights I can subtract from 75? Okay, so what would I do? So I would be an 8. And what does that leave me? And then can't subtract a 4, so I'd put a 0 right there, right? And then I'd come over here and subtract a 1 and a 2. And that would be the output of the A to D converter when it saw 3 volts. So the weight that we're getting out is actually no real indication of the actual value. Then my computer would have to take this and figure out what that was, what that represented. So all an A to D converter does, and the more steps the A to D converter has in it, the better the resolution it has. So if I took 10 volts and we call it a degree per step. How my fuck's the generator down? Oh, it's one. Okay, guys, y'all.
Yeah, you got to. I relocated the barbecue. That worked. Oh, put it in place.
So this is a digital scope. But what we're going to do is we're making it measure an analog quantity, right? So it's got a device in there called an analog to digital converter. But what I want you to look at is this guy here is generating a beautiful sine wave. Or a triangle wave. Let's make it generate a sine wave. Now look at what the scope's giving. Oh, this is AM modulation. Can y'all see the scope? It's doing it in what? Y'all see? I'll see it in. It's doing it in steps. Can y'all see the steps? Y'all look close enough. See, it's doing it in steps. So it don't know the difference between this step and that step, so the display is actually jumping in steps. Because it's going through an analog digital converter. And the converter sees it as volts per step. Right? You understand that? You know? Turn this guy here off. See the steps? So if I did this on an analog scope, that would be beautiful and nice and smooth. A digital scope is going to take that and display it in steps because it's going through a lot. It's going through an analog to digital converter, which means we got so many volts per step. So it's moving in steps. Even though the signal itself is not moving in steps, the computer is going to see it in steps. So it goes to the A to D converter. It comes up with a number that represents that vote. And then it switches it up to whatever step that represents, right? So we've got so many steps that it's displayed. I don't know if it gives me. I think if I go to I'm changing. And you can see if I change the volts, the step size is actually changing. Because what we're doing is just blowing it up. So that's one of the disadvantages of analog digital is that we will never actually be able to truly represent the analog signals that we're measuring. Because analog, if I say a pot goes from 0 to 10 volts, and I'm good enough, I should be able to get an infinite number of voltages between what? 0 and 10. Digital, we don't deal with infinity because we have to make. So analog, we can deal with infinity, right? You understand that? Y'all understand that? Digital, we can't, because digital is going to be represented by a number, and we can't have an infinite number. So somewhere we're going to have to give up on the resolution of the digital sensor, and what it is, it's the number of bits. If it's an 8-bit analog to digital converter, then the best we can do is 255 counts. If it's a 10-bit analog to digital converter, then we get 1,024 counts. If it's a 12-bit, then that would be 4,096, right? So I would take 10 volts and divide it by 4,096. So I would be able to represent them a lot more accurately, but it would be a lot more expensive. Okay, guys, what do y'all think about it? So that's all analog to digital converters do. We have the counter type, which basically starts a counter running. And then it's got a comparator. And it raises an output voltage. The counter is going through a digital to analog converter, and it's raising the output voltage. It's comparing that to the voltage coming in. When they match, it stops counting. Then it just pops that up on your meter. Then it resets to 0 and starts counting again. And so the output of the counter is going through a digital to analog converter is coming into the input of a comparator. It's latching the input coming in from your unknown on the other input, and it just starts counting. And so as soon as the output of the count matches the input, that's when your meter just does what? Pops it up on the screen, then does what? Resets the counter and starts all over. And if it counts all the way up to 2,000, and it never got a match, it ranges it in. It reduces the input. It divides the input down, right? You understand? So it might divide it by 10, the unknown by 10, and then it moves the decimal point over on your meter, starts counting again. If it don't get up to 2,000, if it gets up to 2,000 counts and doesn't get a match, what does it do? Resets it again and redoes the reference, and then starts counting again. So this is why D to A is so dang slow. Digital meters are slow. I mean, you can see them. You can see this. You can get it. You can put it in there. You know, if you look at it on the scope, you'll see if you change stuff, it's changing instantly. So I could come over here on my scope and change the voltage, and it's doing this, right? But on your meter, since it's going through a count, it's going through a 2,000 count. 6,000 count would be a lot longer, right? If they counted at the same speed, but they don't. Okay. All right. Y'all can step back now. Let's see what this class gets out at 12:45, right? Yeah. Almost.
We got this one sitting. It was simple.
Okay, so the next thing we're going to look at, we're going to start into encoders. And we have two types. We have what? Absolute and incremental. This is basically what an encoder does, a position encoder. And you'll see basically how it works. So we have a light source. And what's a photocell? What's a photocell? It's a device that receives light. It's technically referred to as a photoresistant cell. We have two types. Generically, we call them solar cells. What's the solar cell? But it absorbs the energy from the sun and converts it into photon. Those technically called photovoltaic cells. I always say it wrong. A photocell is basically a resistor that's sensitive to light. So when light strikes it, its resistance goes down. When light doesn't strike it, the resistance goes up. My meter. Somebody go get my meter off the line.
Light,
My meter.
light goes up.
Goes down. We got one over here. Y'all come over here. So if I go, let's tell you. This is typically line. This is same stuff in all cases, right? Go out to any one of these lights out here, turn on at night, climb up there, on the glass and now of course these guys right here can't turn on it right off and on. It's simply dark, it's simply light. Bring that into some type of bulb light that connect with this for that flash. These guys, this is a photo. So what's in motion? Come up here to one setup. The light source on one side, photo on the other. Every time it's on the flash, water rod, every time you have a trouble, that's like, so what would happen is, like, bolt and the pole, so the smaller we can make these blades, the more the texture of that. What? Those lines have a magnified like a direct line so close to get up normal robot. So usually you buy you just slap it on. Code that side off. Sometimes I have a flat. You do have needs to check on those. Just photo guys. Instead of what students keep kind of focused. So how do I have? Yeah, it's going to be relevant to something. You understand that? A lot of your printers, what we do is these guys have to start with the board. I know print on sign zero. Once it's found zero, so I have a sensor up here, it's up and that zero, right? And once it knows zero for that hit zero, then it can count every pulse, every zero. Like I said, nobody. It's just a lot. So what happens? Others is turning one thing. And you got the code. This is for a situation where we're going to find out a lot of sensors actually multiple devices. So here, this would be a coder, but that means nothing unless I have an optical sensor. We combine it with a photo sensor. Now we have a encoder. So here's nothing. Right? So you're going to find out a lot of our sensing elements, like boron, stuff like that. The sensors themselves don't. They're amplified. Then we'll hook up another sensor, right? And then the output of this. So we have what we call boron. That plane is on the surface. The pressure. Okay, but how do I do that? Well, I might put here a pod. So a pod is a position, but it's not actually sensing the wave, it's just sensing the position. The boron tube itself is nothing unless I do what? Unless I look at the pod up there. Now when the boron tube starts to straighten out, it's going to turn pod. Pod will turn both and now for a lot of our sensors, you're going to see some mechanical that senses. Then we're going to run into another one of our sensors that we want to talk about that actually does the conversion between mechanics. So, there you go. Okay. Y'all in? Third. No, this class does not give a hospitality, man.
And this will be on Facebook. Facebook.
This will be on Tegrity. This is on Tegrity.
Yeah.
And I'll try to get the. We have a 4-day weekend, so I'll try to get these slides up there by through the weekend. Okay.
Oh.